Now that we've covered the kinematics of rotational motion, we're going to move into dynamics. And just like we did when we moved into dynamics for translational motion, we're going to move into dynamics of rotational motion. So when we were looking at translational motion, we discovered that the force is a cause of translational motion, and that's governed by Newton's laws, and specifically the force, and the net force is directly proportional to the mass times the acceleration that the object experiences. And that if an object is not experiencing acceleration, then inertia does in fact take over. So here's our key idea for this lesson. Torque is the cause of rotational motion. So force is the cause of translational motion, torque is the cause of rotational motion. And so we're going to dive right in and take a look at what torque is. When you're going to make an object start rotating around an axis, you have to apply a force. But it matters what kind of a force you apply. The direction matters too. If we had a flat disc that was in plane with this paper, and I pushed down on the axis for this, it would not begin rotating. Likewise, if I pushed back on it, it would not begin rotating. It's going to take a force at the edge of this particular wheel in order to begin the rotational motion. So that means that where I apply the force and how I apply the force is going to matter to actually cause it to accelerate in a rotational way. So where the force is located and the direction of the force is going to be important when we're looking at what causes rotational motion. So let's take, for instance, an example where we're looking at a bird's eye view of a door. And here's the wall, here's the hinge, and here's the door. The nice thing is that if we're looking at this door, the hinge right here is the actual cause, or the actual point about which the door will rotate. So that makes this hinge the axis of rotation. And if we're looking straight down, we can see that you have a force being applied close to the hinge and a force being applied close to the doorknob. And intuitively, I'm certain that you know which of these forces is more effective. The force that was given, so even if FA is equal to FB, right, they're the exact same value. If you apply the exact same value force here and here, you know that the force at position A is going to be more effective than the force that's given at position B, which means that it's more than just the size. Applying the same force with a different distance away from the axis of rotation is going to be more or less effective depending on how far away. You know that scene from Jurassic Park where the raptor is trying to get into the computer room and Grant is holding the door closed and Ellie comes and she's going to help him, and Grant's here pushing on the door here, and Ellie goes right here, right against the axis of rotation, and she's pushing, and she's like, I can't get the gun unless I move. And that's silly because even if she was applying her whole body weight right there, it was absolutely useless. So what that tells us is where the force acts, as well as the magnitude and direction of the force, affect how quickly the door is going to begin to rotate. So where we place the force, here compared to the axis, here compared to the axis. The magnitude of the force, whether this force is larger than this force, and the direction of the force, whether we're pointing straight onto the door or straight into the door, are all going to change how fast that door rotates. So we're going to have a little bit of a truth, and we can confirm this and we can show it experimentally, and we've got some previous experience in our life that also determines that this is true, and that is that the angular acceleration of an object is going to be proportional to the force, right? You apply more force, it's going to rotate more quickly. It's also going to be directly proportional to the perpendicular distance from the axis of rotation to the line along which the force acts. So here we've got a reference to the axis of rotation, and we're saying that acceleration is proportional to force, which we expect. And it's proportional to the perpendicular distance from the axis of rotation. So let's take a look at that. The perpendicular distance from the axis of rotation would be the distance for object B from here to here. And for object A, it would be from here to here. So that's the perpendicular distance from the axis of rotation to the line along which the force acts. What do I mean about the line along which the force acts? Well, that's the direction of the force. That's the vector direction of the force. That's how the force is acting. And if you notice, this RA here is at a 90-degree angle to the direction of the force, and this RB here is at a 90-degree angle to the direction of the force. So that would be the perpendicular distance from the axis of rotation to the line along which the force acts, and that has a name. We're going to call that the distance from the axis of rotation to the line along which the force acts is called the lever arm. So that means that RA and RB actually represent what's called the lever arm of, there's something stuck in there. Where is it? What the hey? That was awful. Okay, so those are the lever arm. Another term for the lever arm is the moment arm. The moment arm for force A right here is given by this distance right here, which is the perpendicular distance, 90 degrees from the force, coming up from the axis of rotation. The moment arm for force B is this perpendicular distance between the axis of rotation and the force. So here now we have a relationship. Remember, these are directly proportional. So that means that if RA, the lever arm for the force A, is 3 times the lever arm for RB, right? This is 3 times the distance. Then that means that the acceleration given by this situation at A is going to be 3 times the acceleration of this situation over here. Another way to say that is that in order for them to have the same rotational acceleration, in order for them to rotate just as quickly about the axis, the force given here at point B needs to be 3 times the size of force A in order to cause the same rotational acceleration, all because the difference in the lever arm. So there's the mathematical relationship between acceleration, force, and lever arm. So we're going to put it together as a proportionality. The angular acceleration is proportional to the product of the force times the lever arm. That's what we're saying. So we're going to give force times the lever arm its own symbol. It's tau, and that tau stands for torque. So that means that force times lever arm is equal to torque. And we know that torque, or these two values, are directly proportional to the angular acceleration. So that means that angular acceleration is proportional to torque. Just like in translational motion, there was a relationship, a proportional relationship between acceleration and force. And the connection value here is that force is directly related to mass times acceleration. Here, we don't know what the connecting point between rotational acceleration and torque is, but we know that it's a direct relationship if torque is given by force times radius. So let's take a little bit of a look at the moment arm. The lever arm is the perpendicular distance from the axis of rotation to the line of action of the force. So let's take a look at what that means. Right? The torque for force D would be given by the force of D times the lever arm for D. Torque for C would be force of C times the lever arm for C. And the force of A would be, torque of A would be force A times lever arm A. Now let's do some simple work first, right? Here, force A is acting along this line. So here's the line of action for force A. At a direct 90-degree angle then is this measurement here, R. So that's RA and FA. They're already at a 90-degree angle to each other. So FA, RA are already at a 90-degree angle to each other. So we could take the value of FA and the value of that distance along the door, and we would get the torque for object A. Force D is directed straight along this point, along the axis, into the axis of rotation. Here, that means that any sort of radius would have to be along this perpendicular line, and there is no amount of separation that is perpendicular. So that means that that value would have to be 0. This force right here would not cause a rotation. Force of C, the line of action, is actually at this angle. Right? So that line of action can be seen here. And we know that that line of action for that force has to be at a 90-degree angle to the radius. So the radius connects the line of action to the axis of rotation. So we could draw a line from the axis of rotation and meet it up with the line of action for the force C at a 90-degree angle, and that is how we're going to find the radius or the lever arm for point C. So that means that this is RC, not this. And so you're actually going to have to find that connection point between those two values. So that can be given here as torque is given to as the perpendicular lever arm times the force, or the perpendicular of the radius here. Here's the radius. We need to find the component here. You've got a component. If this is the radius, here's our y and our x. So we're actually looking for the perpendicular component of the radius. So one of the things that you're probably thinking is well, why am I having to draw a line of action, and why am I having to find that radius, when wouldn't it be easier to just determine, I know that this component of FC is not going to do anything to rotate the door. It's only this component right here that's going to do the rotating. So why don't I just find that component right there? And that's totally fine, you can. But what's actually going to happen is you're going to see that this is a similar triangle situation. Right, where if that's theta here, then you're going to have a 90-degree angle there, 90-degree angle there. That's also theta. If that's theta and that's theta, then that means that coming down this line, we're also going to have that as theta, and that is your opposite angle. So that means that if we've got similar triangles, this and this are similar triangles, if I want to find this component for the lever arm, or if I want to find the acting component of the force, I'm actually looking for the sine of the exact same angle. So that means that if that's theta there for finding the perpendicular lever arm, and that's also theta there for finding the perpendicular force, that theta and that theta are the same amount. So that means that I could find torque by finding the perpendicular lever arm, or I could find torque by finding the perpendicular force. This is going to give us the same value. Since this angle is opposite of my unknown, and this angle is opposite of my unknown, whether you use this equation or this equation is a moot point, because it's the same angle, this and this, and it's given by opposite to that angle, or sine theta. So that means that you can, under every single circumstance, find torque by finding the perpendicular between the radius and the force. And that sine theta could be used to find the acting component of the force or the acting lever arm for the rotation. And that equation is all you're going to need. So let's go ahead and let's take a look at some simple examples of how this is done. Here we've got an arm, and I'm going to zoom in on our arm because it's actually a little bit small. But our task here is if the bicep, which is given right here in the image, can apply a vertical torque, that means a vertical force. That means that no matter how the arm is bent, the bicep is going to apply a perfectly vertical force. And we're going to say that this particular bicep, which is rocking, has a 700 Newton force that it can apply upward. We're going to compare the torque when the arm is bent at a perfect 90-degree angle and when the arm is dropped 30 degrees below the horizon. And we're going to use those values to determine at what point in time can your arm apply a more effective, your bicep apply a more effective torque to, or create a more effective torque to move your arm. So remember that our torque is given by the equation RF sine theta. And since our torque is given by that calculation, then we can go ahead and we can dive straight into A. One more piece of information here is that they said that your elbow is the axis of rotation, and the muscle is attached at a 5 centimeter away from the elbow value. So here, R is going to be equal to 0.05 meters. And F is going to be equal to 700 newtons, and they are currently at a 90-degree angle to each other. So calculating the torque for A is just going to be RF, or 0.05 meters times 700 newtons is equal to 35 meter times Newton. Those are not Newton meters, those are meters times newtons. Those are the units for torque. Do not get them confused with the units for work and energy. Alright, so that's A. It's incredibly straightforward, but for part B, the elbow is dropped 30 degrees below the horizon, so your hand has been lowered, and your 5 centimeter separation is now located there. It's no longer, you can see it's no longer at a 90-degree angle to the force. And so we're actually going to have to now find the angle of separation between the two so that we can find the new torque. And there's two ways to do it. I'm going to draw these in larger. So in both situations, you know that the force is up. In one situation, alright, the radius, instead of being along this perpendicular, it got dropped down. Alright, and it got dropped down, that down amount is 30 degrees. And so now, that means that right here, this value right here, is 60 degree. And that's your R. We want to find the perpendicular. So that means we're trying to find R perpendicular. Alright, R perpendicular is opposite to 60 degrees, so that means we can find that as tau equals RF sine of 60. And that's for finding the perpendicular lever arm. But let's say we were just interested in the force. Remember, the force is up like this. It's attached to our lever arm R there, which was dropped 30 degrees from the horizon, which means that your angle of connection there is 60 degrees. That makes this our perpendicular force, and by similar triangles, 30, 60, that will be given by the sine of 60. So whether we're looking for the perpendicular component of the force or the perpendicular lever arm, we end up with sine of 60. And we can find the torque is RF sine 60, so that means it's going to be 0.05 meters times 700 newtons times the sine of 60, which gives us the value of 30 meters times Newton. And that's what our torque equals for part B when it's dropped below. So you can see that compared to part A, we've actually lost some of our torque because we've shortened. Right, this component of the lever arm is shorter than the lever arm when it's up. So you have less torque, less ability to apply an effective force when your arm drops below a 90-degree angle. And that could explain why you can do lifting better in some positions than in others. Let's take another look at another situation where we can compare torques. And here in this situation, I give you that this ruler is going to be rotating on an axis, right? And I apply FB at the midpoint and FA at a 30-degree angle to the very tip. And if FB is 20 newtons and FA is 30 newtons, which force exerts more torque? Well, we know that force times the perpendicular radius, or FR sine theta, is going to be equal to torque. So the torque given by force B is going to be RB times FB. And I also know if this is the midpoint that RA equals 2RB, because it's twice the distance all the way at the end. So that means that the torque of A is going to be given by, now here's RA, and here is the vertical component or the effective component of RA, which is going to be given by sine 30. So here I can use twice the radius of B, 2RB times FA times sine of 30. And now I'm comparing RB times 20 to 2RB times 30 times sine of 30. And I can actually compare and see which one's more effective. So the sine of 30 is 0.5. 0.5 times 2 is 1. So RB 30 newtons equals the torque of A. RB times 20 equals the torque of B. Now that we've got these two values, we can compare them, and we can see that even though the force of A is given at an angle, since it was a larger force with a larger lever arm, it's going to end up being a more effective value or have more torque. So we've been just comparing one type of torque to another type of torque to see what its effect is going to be. But just like in life there's more than one type of force, we're going to have situations that involve more than one type of torque. And when more than one type of torque act, we're going to have to find the sum of all of the torques, or net torque. In order for that to work, that means we're going to have to assign positive and negative values to our torques so that we can figure out if the torques are additive or if they are subtractive. So we're going to assign for rotation. Counterclockwise is positive and clockwise is negative. And so you look at a situation, you decide, is that force going to cause it to rotate clockwise or counterclockwise? And you assign a positive or a negative value as necessary. And so let's go ahead and let's take a look at what that's going to be like. Here we're looking at torque on a compound wheel. And we're given that these two disks are attached to each other and both are going to cause a rotation. RA is 30 centimeters, RB is 50 centimeters. FA and FB are the same value. They're 50 newtons. FA is applied at a perfect 90-degree angle to the line of action, radius A. FB is actually applied at a 30-degree angle above the horizon for RB. So we're also going to need to look. FA is going to cause the wheel to rotate counterclockwise. FB is going to cause the wheel to rotate clockwise. So we've got a positive and a negative torque. The sum of all torques will be torque from A minus torque from B, because B is given as a negative value. So torque A is given as FA RA, where your angle of separation is 90 degrees. So you've got 0.30 meters times 50 newtons equals. And the torque for object B is given by FB RB, and we're looking at either we can determine what the lever arm is compared to this. Here's the line of action, so we could in theory find that line of action, or we could just find the component of the line of action that we're interested in, and the component is opposite to this angle, so that angle is a 60 degree. Likewise here with our similar triangle, we've got 60 degrees here, 30 here, so it's going to be sine of 60, and so that's going to be 0.50 meters times 50 newtons times sine of 60, and we can plug that into our net torque equation. Net torque is going to be equal to 0.30 meters times 50 newtons minus, because the other one is in the clockwise direction, 0.50 meters times 50 newtons times the sine of 60. And when we calculate that out, we end up getting a negative 6.7 meter times newtons, which means that overall the net torque is working in the clockwise direction, and this object is going to accelerate rotationally in the clockwise direction. So what about forces that tilt an axis, or forces that aren't directly perpendicular here? Right? If I've got a force at an angle, right, that force that's going to act above or below this axis of rotation here is actually going to cause the axis to tilt. But tilting is not rotating, so you can't count any force that doesn't act at a perpendicular. Only the perpendicular force that's in this plane of rotation right here will cause an object to rotate. So that is the only force that you can calculate or use to calculate for our torque values. Coming up in our next lecture, we're going to be taking a look at what occurs, or how we're actually going to calculate for the acceleration, because we've ended just knowing that torque is proportional to angular acceleration. We don't know how it's proportional just yet.